Hello everyone and welcome to this lecture. So we had started the journey of algebraic connectivity, which is nothing but the second smallest eigenvalue of the Laplacian matrix, and then we talked about a corresponding eigenvector of algebraic connectivity, and which is known as Fiedler vector. So we have seen some results just by looking at the entries of Fiedler vector, whether the corresponding subgraphs made from the vertices whose indices are on those on the Fiedler vector, whether they are connected or not. We have seen that they are indeed connected. If you talk about all the positive entries, in fact all the non-negative entries, the corresponding vertex set actually induces are connected subgraph. Similarly, if you talk about all non-positive entries, the corresponding vertices induces again a connected subgraph. Then in the last lecture we talked about one bound on algebraic connectivity, and that bound was, I will sorry write what that bound is. Okay, now in today's lecture we will make use of that bound to give some more corollaries of this in terms of the relation between basically the algebraic connectivity and maybe the minimum degree. What about the average degree of induced subgraph of a regular graph, and then we will again talk about the isoperimetric number, whether we can have some bound of isoperimetric number with respect to the algebraic connectivity. Okay, so let us start with the where we left in the last lecture. So let me write the establishment of the basically the algebraic connectivity, the bound on algebraic connectivity. Okay, in terms of the number of edges, then the size of vertex set and distance between two vertex set. Okay, so let us start. Let me first write down. So we have established that. So suppose v1 okay, so v1 and v2 are two disjoint vertex sets. Okay, two disjoint vertex subset rather. Okay, and suppose d v1 and d v2 denotes the distance. Okay, so this was the distance between the minimum distance in fact between any two vertices. So one vertex is in v1 and one vertex was in v2, so such pair, so we will see the minimum distance between any such pairs. Okay, so this d v1 v2 denote that. Then the algebraic connectivity, this mu was always less or equal to this quantity 1 divided by distance of v1 v2 square of this. Okay, and then this number. So this expression was slightly lengthier. Okay, but we will see very crisp corollaries of this expression. Okay, so this, and then this terms were this whole term was multiplied by this, right? So edges in G minus, okay, so edges in G1 and edges in G2. Okay, where G1 G2 are nothing but induced subgraph on what is V1 and V2. So G1 G2 induced subgraphs. Okay, so we have established this in the last lecture. Okay, today we will make nice corollaries of this, consequences of this. Okay, so the first consequence is, so let me write it here. Okay, the first one is, suppose, so let me write as a corollary rather. Okay, corollary. Okay, so corollary, yeah. Let G be a connected graph again. Let G be a connected graph with the minimum degree delta, with the okay, on maybe n vertices first. Let me write, because I will be using the size of this graph. Okay, on n vertices, okay, let delta be the minimum degree of G. Okay, then we can establish that then mu is, the algebraic connectivity is always less or equal to n divided by n minus 1 times delta. Okay, so how to prove this? This very simple looking inequality. Okay, so let us prove it. Okay, so let V be a vertex. Let V be a vertex having degree delta. Let V be a vertex. Okay, vertex having degree degree delta. Okay, so basically the situation will be like this. Okay, so there is a V. Okay, and there are delta edges going out of this. Okay, now suppose by default this is V1, so this is suppose V1. Okay, and rest of the vertices are actually, let us consider rest of the vertices as V2. Okay, now let us apply our theorem that we have proven. The just I have written it down. So by the way, what is the distance between V1 and V2 here? The distance is nothing but 1, right? So distance here is, you see the distance between V1 and V2 is nothing but here 1. So the expression becomes very, very simple now. So this will be equal to, so let me now write it. So this is less or equal to 1 divided by 1, because the distance is 1. Okay, times 1 divided by mod V1, so which is nothing but again 1. Okay, plus 1 divided by the number of vertices in V2. So how many vertices are there? So there are n minus 1 vertices. Okay, times what will be the edges? Okay, so remember this term tells what? This term tells the number of edges which are in between V1 and V2. Okay, so right now you see that number of edges between V1 and V2 is nothing but delta. Okay, so delta is this. Okay, so times delta. Okay, and now it is very, very straightforward. That's this, right? So this is nothing but n divided by n minus 1. Okay, and very, very, very simple proof. Okay, okay, very good. Now think about the case where this inequality is tight, where this is strict. Okay, so we will consider such cases in our tutorial and assignments. Okay, very good. Now let us move to some result using basically algebraic connectivity on our regular graphs. Okay, so let me now write another theorem, or maybe corollary. Okay, corollary. Okay, so let G be a regular graph now. Let G be, okay, so let G be a regular graph. Okay, so let G be a regular graph. In fact, K regular graph. Let me write. Let G be a K regular graph. Okay, so let me write it. Let G be a K regular graph. Okay, and let H be an induced subgraph on P vertices. Okay, in fact I be a K regular graph which will be a connected rather than, okay, connected, because we have established the result for connected graph. Okay, and let H be an induced subgraph on P vertices. Then can we write something about the algebraic connectivity of bigger graph in terms of the average degree of your H? What can be the result? Okay, so the average degree in this case will be the average degree of H. Remember, H is an induced subgraph. We are talking about the average degree inside S, not overall. Otherwise, it's just K, right? So we are just focusing on. So you are basically H is our induced subgraph on P vertices. So we want what will be the average degree. So this is at most. Okay. So any guess? So what will be this? So at most P times mu divided by n, and then you subtract mu from its degree, so plus K minus mu. Okay, so how to prove this? Nice. So maybe I will make it with a small, yeah. Okay, P. Very good. So proof is this. Proof. Okay. So let V1 consist of all the vertices of H. Okay, so so basically all the vertices in H is nothing but V1. Okay, and V2 is rest of the vertex, and V2 is basically vertex set of maybe you can call G minus H V2. Okay, now again if you see the distance is what? The distance is distance between V1, okay, and V2 is equal to 1. It's like this. So this is some H here. Okay, so this is H. Okay, and this is okay, so maybe this is called V1, this is V2, and this is G minus H. Okay, so there will be edges. So distance is actually 1 here. Okay, now how many number of edges are there? How many edges are there? Okay, can your inequality help us? Can your inequality that we proven in the last day, can it help us? Okay, so indeed it will help. Okay, so remember we know that the mu is always lesser equal to, now remember here because distance is 1, so I'm actually ignoring that fact, and this is, so here actually this is the p number of vertices, this is 1 minus p. Okay, so you can actually write 1 divided by p plus 1 n minus p. Okay, so by the way here it will be n minus p, right? Yeah, sorry about this, n minus p. Okay, times the number of edges which are going from h to its complement. So let me actually write it as eh. Okay, or maybe I mean correctly it's h bar. Okay, so this is this, I mean maybe this is the correct one. Okay, so h bar, or okay, so let me write this mod e, which are edges, number of edges which are going from h to its complement. Okay, so very good. So basically it tells that the number of edges are at least, okay, so the number of edges that are going out of v1, so the number of edges going out of v1, okay, are at least how much? Okay, so this quantity will be so on the, if you saw this, the denominator will be p into n minus p, but the numerator will be equal to n, so you will transfer towards the left side, so this will be at most. Okay, so mu times p into n minus p divided by n. Okay, now very good. So these are the, at least this many edges are between which are going basically from h. Okay, so this is h, these are the at least number of this. Okay, now let us calculate the average degree. So we want to know what average degree of this, we want to know the bound on average degree of h. Okay, so if you see that how many so in order to find the average degree here, we want to know how many outside edges are there which are going from this. So this will be not counted when we are taking h as an induced subgraph, right? So we have to remove those edges, we have to actually subtract those edges from all possible edges. Okay, so the average degree will be what? So basically the every vertex here has degree, how much? This is k, right? And how many vertices are there? So that p into k will be the total degree, but out of those connections we have to actually remove those connections which are not in the induced part, right? Which are not in the induced part, and which are what? So p into n minus p. Okay, so this will be at most, so basically the total degree will be, the total degree will be at most this number, due to this, right? So now it is very straightforward. Hence the average degree is, of h of induced subgraph, right? Of induced subgraph h is at most, okay, at most you divided by the number of vertices, which is nothing but k. Okay, so let me write, so 1 divided by p, this is pk. Now let us open it. So mu p, because n will be cancelling out here, okay, and then plus mu p square n, right? Mu p square n. Okay, now the result is very obvious here. So which is equal to k minus mu, okay, q minus mu plus mu times p by n. Okay, so this is at most this. Okay, and then we have proven this result. Okay, very simple stuff. Okay, now let us move to our last part for the day. We will revisit the isoperimetric number, or the Cheeger's constant, or expansion ratio, that we have actually defined for D regular graph in when we were talking about expander. But this is actually a generalized definition. You can define it for any graph. We will prove here that the expansion ratio is at most the half of the algebraic connectivity. Okay, the algebra, so at least the pardon me, so the expansion ratio is always greater or equals to the half of the algebraic connectivity. Very, very beautiful fact. We have proven it for d-regular case, right? D-regular case. But now using the theorem that we have proven the last day, okay, we can actually immediate see this as a corollary. Okay, so let me now write again the third corollary. Okay. Okay, so let HGB rather than a smaller h, okay, sir, be the expansion ratio of G. So let me recall what expansion ratio is. So let me here, okay, so expansion ratio or Cheever's constant or isoperimeter number. Expansion ratio was what? Okay, so it was nothing but minimum over all possible. So remember this the boundary of a subset. Boundary of subset means number of edges which are going from S to its complement divided by the size of this, and this S is actually less or equal to n by 2. Okay, so this was expansion ratio. Then the expansion ratio is always greater or equal to the half of the algebraic connectivity. Okay, so how to prove this beautiful fact? Okay, so let us prove this. Okay, so let us prove this proof. Okay, very by the way straightforward. So we know that mu is what? So mu is actually, let me again write, so 1 upon v1 v2, okay, and then square times then 1 mod v1 plus mod v2, okay, and then the number of, multiply the number of edges, okay, number of G2, okay, so where G1 G2 are actually the induced subgraph on V1 V2. Okay, very good. So now if you see that, so let's suppose this Hg in the definition of Hg, so suppose S is that subset which is actually giving you that minimum ratio. So suppose this is S, okay, and this is V minus S, right, and these are the edges. Okay, so basically delta, this is rather than, so this is delta S, which is actually boundary. Okay, so this is delta S. Now you see, and the distance between S and V minus S is nothing but 1. So this can be written as simply this divided by 1 mod S, okay, plus V minus S, right? So mod of this V minus S, okay, very good, and then times delta S, right, times mod of this mod of delta S. Okay, so mod of delta S. Very good. Now you see that S here is less or equal to n by 2. Okay, less or equal to n by 2. So that means this quantity will be more basically greater or equal to n by 2. Hence this total quantity will be lesser than this, right? This part. So we can actually write this as is actually 1 mod S plus again mod S, right? And then this quantity mod ds. Okay, and now this is very straightforward. Okay, so this quantity is now equals to, if you see that, 2 divided by mod v1 times so mod this. Okay, so now what is our equation, inequality? So this mu is less or equal to 2 divided by mod v1. Okay, this. And by the way, this number is what? This number is nothing but Hg, which is nothing but Hg, right? So 2 times Hg. Okay, 2 times Hg. Hence, this implies that Hg is always greater or equal to mu by 2. Very simple proof. Okay, very simple proof. Yeah. So I hope you enjoyed this very simple corollaries coming out of the very nice bound on algebraic connectivity in terms of distance of two vertex sets, 2 subsets of vertices, and then the number of edges which are going in between these 2 vertex sets. Okay, and of course the size of vertex sets also. Very good. Okay, so we will see some more results on algebraic connectivity, some more bounds. Okay, okay, so thank you very much and see you in the next lecture. Till then.